Alright, so in this video I'm gonna be explaining another important article on model editing with the title Model Editing with Canonical Examples. This paper in 2024. So we introduce model editing with canonical examples, a setting in which a single learning example is provided per desired behavior. Evaluation is performed exclusively out of distribution, and deviation from any initial model is strictly limited. A canonical example is a simple instance of good behavior. For example, the capital of Mauritius is Port Louis, or bad behavior. An aspect of researcher is cold-hearted. The evaluation set contains more complex examples of each behavior, like a paragraph in which the capital of Mauritius is called for. We create 3 datasets and modify 3 more for model editing with canonical examples, covering knowledge-intensive improvements, social bias mitigation, and syntactic edge cases. In our experiments on Pythia language models, we find that LoRa outperforms. So I explained LoRa in the previous video, I guess. It outperforms full fine-tuning and Mimit. We then turn back to the backpack language model architecture because it is intended to enable targeted improvement. The backpack defines a large bank of sense vectors, a decomposition of the different uses of each word, which are weighted and summed to form the output logics of the model. So you see, the model editing with canonical examples provides simple examples of good or bad behavior, a goal, and a language model, and evaluates more complex examples of that behavior. Updated models cannot increase in loss on a general corpus more than an epsilon factor of the base model's loss. For example, you have a base language model. Your canonical example is the capital is Yaren, for example. But the goal is to increase the probability, or sometimes balance probability, or decrease it. And then you have this updated language model. So let P theta be a distribution over V star, as well as conditional distribution of a symbol following a prefix X. We refer to pre-trained language model before any updates on canonical examples as P theta. And T is a set of prefixes, X sub I, continuation option yi sub a, this is continuation options, continuations options b, and the loss function L sub I. Either of the 2 continuation options may be null. Intuitively, the loss functions may specify that y sub a is good and no y sub b is provided. For example, the capital of child is y sub a. We know that such a loss might just be negative like likelihood function. For another example, we may want the probabilities of the 2 continuations to be balanced without stating preferences on the probabilities of other continuations. For example, in X, we have the nearest set, and YA is she, YB is he, the continuation. So such a loss might be represented like this. But there are other losses that are in table 1. For example, this loss, or even this one. There are different losses that you can use. So we always have a canonical and the evaluation. for any task. So, whereas T is drawn from a simple canonical distribution, the evaluation set is drawn from different, more complex distribution. And we define success criteria, which evaluates that the loss function on the examples and evaluates whether that loss is less than the threshold. So we use a threshold like this because in naturalistic setting there is no single correct continuation. And then we have this important degradation balls. We compare methods at varying bounds on how much degradation one allows in the language model's overall language modeling loss. We call these degradation balls. On a general corpus G, we estimate the overall language model loss of p theta as well as the original model p theta 0 and define the sets of models that achieve at most a factor 1 plus epsilon of the loss of the original model. We use a multiplicate bound on the loss since the difference of this loss is more meaningful for a model with, for example, a loss of 2.3 than one with loss of 3.4. In addition to our main evaluation, we draw from the model editing literature and define a dataset of hard negatives. Even in curriculum learning, we have some hard negatives, hard examples. And these are 6 datasets for model editing with canonical examples: country capital, company CEO, stereo set, pronoun gender bias in carriers, temporal entities, hard syntax. So for fine-tuning, we call fine-tuning all parameters of a language model full fine-tuning. Full fine-tuning seems likely to overfit, but certainly has the capacity to adapt the model in general. And we use this KL divergence between p theta 0 and p theta. You see that LoRa fine-tuning can be represented like this. For a set of matrices M1, Mk, the updated matrices are this. And MEMIT can be formulated like this. Mass editing memory transformer, we call it MEMIT, is a state-of-the-art model editing method that targets the same MLP parameters as we've chosen for LoRa. So it constructs an edit such that the distribution of MLP key vectors associated with some prefix is associated with new value. So given an association, MEMIT considers the representation H sub I for the last token of S sub I at a target layer. And then they have this backpack language model, which learns a set of K-word to vec-like sense vectors for each element of the vocabulary. And D is the model commons vector dimensionality. To construct the distribution, the backpack weights and sums the sense vectors of the words in the prefix. This is the sense vector of word J, and this is the weighting of that sense in prediction. And then we have sense fine-tuning. We score each sense vector for a single example. But most parameters of the network are frozen. So in sense fine-tuning, a handful of sense vectors are selected based on an estimate of their importance to the canonical example relative to general text. The gradient of the loss canonical example with respect to sense vectors chosen for training is much like that of word2vec. So due to linearity, the senses are simply updated to point more in the directions of the word embedding of target words. The strength of their update depends on alpha, the weight they are assigned in backpack sum. So due to sense vectors combining log linearly for prediction, whenever these updated senses are assigned high alpha by the backpack at inference time, the effect of fine-tuning is the same, which is to increase the score of the word in the canonical example.